So, no, no one listened. On Sunday, there's an SI session, and if you don't like KSP and you don't like buffers and you don't like all of these numbers that you're going to be shown, then you probably want to come because Strav likes it, and Strav will make you like it. Well, she might not make you like it, but you'll probably understand it better afterwards. So 4:30 in the Wade tutoring room.
That's all you have to say? All right, folks. In case you hadn't noticed, there's visitors in the room, so everybody on their best behavior for a change. Yeah, I heard that, Emma. Where are you? I heard you laughing. Yes, you did. See how bad it is once you start saying your name enough times? All right, if you haven't read your observer yet today, make sure you notice there's a quote from your one of your SIs there. Why should you be featured and state your case? Notice who's not here today, by the way. Jessica just walked out on me besides, too. Oh, she's back there. She's back there still. She's about to walk out on me. All right, somebody asked me, are you really going to put thermodynamics on the test next week? Yes, I'm going to put thermodynamics on the test next week. It's going to be a very general introduction. It's going to get you start thinking about that again. It's not going to, I hope, cause you undue hardship. The other thing is, I will be giving you a few more Kappa problems over the weekend. It'll be posted sometime Saturday. Again, it's practice problems for you to be able to get ready for the tests on Thursday. Okay? Kappa, I believe, is due on Wednesday. Oh, we can do a video conference. Cool. Let's do a video conference. All right. Have fun in lab. I've been getting a lot of questions, folks, about, first of all, yes, this is traditionally, thank you, this is traditionally the hardest test of the semester.
Haven't we had suffered enough this semester?
Yeah, don't I get that every test becomes the hardest test of the semester? Actually, the one after this is a piece of cake. I take it easy on you as we go into the final, sort of. No, buffers in general are causing people headaches. And I realize that I can stand up here and make them look as easy as possible. But remember, like I said the first day of class, I've been doing this 20 years. If I don't make it look easy by now, something's wrong. But I tried something new this week. And I want to see if it helps. Thus far, the half a dozen people I've shown it to, it has helped. And it's a different way to approach the buffers. The first question I always get asked when doing a buffer problem is, what equation do I use? Not what mathematical equation, what chemical equation? And what I want to show you is, it doesn't matter. So for example, if I tell you that you've got a buffer system made from ammonia, and ammonium chloride, and you've got 0.7 molar ammonia and 0.65 molar ammonium chloride, as soon as you see that, you have to write a chemical equation. And there's two. Which one you write is up to you. I can either do the logical thing that says, take ammonia, and if you go back and review, you'll always see that I always react it with water. The book doesn't. The book takes acids and dissociates them. I like to react it with water because it's consistent, it works, it's a way that you can always figure out what's going to happen. And so you can write the equilibrium equation for that reaction. Or if you wanted to, you could say, well, I know all chlorides are soluble except silver, mercury, and lead. So therefore, I've got ammonium ions. And so I could do, whoops, that. What I want to convince you of is that it doesn't matter which of these two chemical equations I use, the pH of this buffer system is going to be the same. It's the same system, it better give me the same pH. So my ice table, 0.70, we don't care, 0.65, there is none of that. At equilibrium, we get this, or excuse me, the change that occurs at equilibrium. We have this. Okay? From there, we set up our Ka. Oh, hydroxide's a product, so it's not a Ka, it's a Kb. So we can write the equilibrium expression. We can substitute in the values. From the table. And from here, we have two unknowns still. X is an unknown and Kb is an unknown. We need to know one of them. Well, I'll tell you that Kb here is 1.8 times 10 to the minus 5. So this equals 1.8 times 10 to the minus 5. Emma? Yes.
Don't you then have to assume, like, don't you have to account for that in the second x on the top? So would you be multiplying by 0 just mathematically?
If you, we're going to do that. And I'll explain again why that is. So we make, to solve this, you could either solve your quadratic if you want, or you could say, assume that x now, we're assuming that it's less than 0.65. We're not assuming that it's 0. There's a difference. If we assume that it's 0, then yeah, if it's 0, then we'd substitute 0 in everywhere where there's x, and we'd get Kb equals 0, which it's not. So that can't be the right thing to do. If you assume x is much less than 0.65, what that is in essence saying, oh, is that 0.65 plus a very small number is still 0.65. And if 0.65 plus a small number is 0.65, then 0.7 minus a small number is still 0.7. But x is still a real number. It's just small. And it's not 0. Okay, so that's why you'd have to keep it there. So now we rearrange this equation and we find out that x where's my SIs when I need them? Who's fast on the calculator today? Thank you. Which is the hydroxide ion concentration, because I go back and look at my table and say, okay, X is my OH minus concentration. So I can get my POH. He's just not as quick as the SIs, is he? So the pH is 9.29. If you want to make an announcement, Barack, you're supposed to come before class. I'll take a commercial break in a minute. All right, so now we're going to do the problem the other way. Now we're going to start with ammonium ion and do exactly the same problem, except we're going to use the other reaction. If this is working right, I better get the same answer. If I don't, I'm in trouble. So, ammonium ion, 0.65. We don't care. 0.7, none. Okay, so we've got that. Again, it's just like we've always done it. Remember, the whole point of this is everybody asks me, what is the chemical equation? And I want to convince you it doesn't matter. Pick one and go with it. Actually, pick them both, and you'll see why in a second. Well, now this one's a Ka, and I know that because hydrogen ion is a product. As soon as I see hydrogen ion, I have a Ka. So we substitute everything in again. So far, it's very repetitive. Except now we need Ka. We still don't know X. We don't know Ka. We can look at the problem, and we've got Kb. Because it's a conjugate acid-base pair, we know this has to be true. And so Ka if I did my math right, should be about 5.6 times 10 to the minus 10. Aside here for a second. Remember that the value of Ka being less than 10 to the minus 7 does not indicate that the pH is necessarily basic. It does indicate that it's very, very weakly acidic. Okay, so you're not going to get a lot of H+. So we take this, and we make the assumption. Same assumption, so we get X equals 5.6 times 10 to the minus 10 times 0.65 over 0.70. Oh, he's good now. 5.2 times 10 to the negative 10. We look at the table. X is the hydrogen ion concentration, so the pH. How much? 9.28. And if I've done everything right, that better agree with that. Close enough. Okay? There's round off error in there somewhere. Emma. Uh-huh. Yes. The chart in your book lists both Kas and Kbs. Yes. Yes. If you multiply Ka times Kb in those charts, they better equal 10 to the minus 14. Okay? So you can see it didn't matter whether I started with ammonia or ammonium ion. I knew they were both there because the problem told me that. You can pick whichever one you want to do the problem. And then just write the equation. And as I said, the book for that reaction up here on the right, they would have just taken ammonium ion and made H plus and NH3, a dissociation reaction. I prefer to do it as a hydrolysis, a reaction with water, simply for consistency. Whether I do it as a dissociation where I forget about the water or I include the water doesn't matter. It's the same thing. We're going to ignore the water anyway. All right? So for any buffer problem you get, write an equation. And now I'm going to tell you why you want to write both. Brock, do you want to do a commercial break for me? Sure. All right. Oh, you mean I got to put the screen up? You're going to go online? No. Oh, that. Yeah, come on here. I see, you have a flyer. Push the button on the... I'll do it. Yes, sir. How high, sir? There's a microphone if you want.
Where's everyone?
It's Friday. What do you expect? It's Good Friday besides.
Well,
You don't need this, right?
yeah, I know. Anyway. Well, this Saturday, 8 to 10 p.m., we're having a costume party. If you want to come, and I'll be there, but you won't recognize me. I'll be a Greek goddess, so I'll look something like that without the wings. Food, best costume prize.
You gonna shave beforehand? Your legs, I mean.
I don't know. We'll see. Any volunteers do that for me?
Shave your legs for you?
I can't reach.
Dr. Kenney should do it.
All right, let's now.
I've shaved my own legs, and we're not going there.
Okay.
I don't. TMI, right?
Anyways, you should all come. It'll be good. It'll be fun. Have some activities, food, music. And it's Alumni House, not on the south side, the new one on the north side, where all of you live. So, yeah.
What about squash tournament?
Okay. There's also a squash tournament next the weekend on Saturday, 9 a.m., 10 a.m. till whenever it's playoffs. So you can come, play a game, lose, you're out, or continue on. So we have like a huge trophy, 24-inch, if you win the whole thing. Tennis players are usually good at squash, so you play tennis. And anything else?
Nope, nothing I can think of. That's the only club that I have an advisor for, right?
All right, so you should come. Thanks. Oh, and if you need help for this exam, I have last year's exam, so talk to me.
Yes, Barack does have copies of all of last year's exams, so you can call him for help on the exams. All right. You can cut this out. Is it? No, that one's not an extra credit. Sorry. The reason it's not, I was asked not to make an extra credit. Because the last time you guys did a phenomenal job and ate the Jewish Student Association out of their budget. You walked in, made an appearance, signed the sheet, grabbed some food, and walked out. And I didn't say you had to stay and participate, I just said you had to show up. So they asked me not to make an extra credit this time, but you're still invited to be there. The food is always good. There is also one more party to keep your eye on near the end of the semester that you'll enjoy. All right, guys, your coach is waiting for you. He's in the back. All you can eat cheesecake party. Yeah, that's coming at the end of the semester. All right. Now, why is it helpful in this case to write both those equations? What are you throwing stuff now? Oh, your water bottle. Now the question says, okay, let's go back to the favorite story from Jessica from last year. How many times did I ask the class, what is a buffer? 4 times, they'll tell you. What is a buffer?
Either a weak base that's conjugate acid, or a weak acid that's conjugate base and relatively equal amounts.
Ah, very good. Zane's got it down now. A buffer solution is a mixture of a weak acid and its conjugate base, or a weak base and its conjugate acid in relatively equal amounts. That's a key. That is designed to resist changes in pH upon addition of acid or base. That's the complete definition. The relatively equal amounts is a key because the number of moles of acid and base you've got determines how effective the buffer is. You can make a buffer with a very small volume, or you can make it with a huge volume, and the pH is exactly the same because it depends on the concentration. But when you want to know how long will the buffer last, you need to know how many moles there are. So for example, one of your kappa problems this time says you've got a buffer made up of 2 things, and it doesn't give you a volume. That's a problem. If you go back and look at the problem that it's based on from the text, it says 1 liter, which is nice because then the molarity and the number of moles are the same thing. So that specific kappa question, assume 1 liter of volume, because that is important. But now take this buffer system. I've got a buffer system made up of ammonia and ammonium chloride. I add hydroxide ion to that buffer system. Let's say that I add 0.2 of a mole. Can I do that? Bless you. Yeah, I can add 0.2 of a mole. We'll say there's a liter of solution. Okay? The book does this in a way that I really don't like. The book then uses the ice table to figure out what happens when I add the strong base to it. And that's okay, there's nothing wrong with it. The reason I don't like it is because I'm a creature of habit. I like to use the ice tables as ice for equilibrium situations. But what do we say a buffer problem was? Solve the limiting reactant problem first, then solve the equilibrium problem. Well, the equilibrium problem gets solved using this tool. A limiting reactant problem, you don't use an equilibrium table, an ice table. We never did, so why should we start? So if I add 0.2 moles of hydroxide ion, first of all, when we add hydroxide, what's going to happen to the pH? Is it going to go up or down or stay the same? It has to go up. If you ever find out that it goes down, something's wrong. So you add strong base, the pH better go up. So the question now is, when you add hydroxide ion, what's it going to react with? Now I'll tell you, if you ask last year's class, they will give you a very circuitous discussion of what it reacts with. It was perfectly correct, but it was also extremely confusing. So I've never told you this, and I'm not going to today. Maybe after the test I'll explain it to you. But if I look at the two reactions, remember I can pick either one, and I say, okay, I'm adding hydroxide ion. What does the hydroxide ion react with? Well, it tells me right there. It reacts with ammonium ion. Ammonium ion plus hydroxide ion reacts, and what do they make? Ammonia and water. So if I add 0.2 moles of hydroxide ion, and I picked a liter intentionally, to 0.65 moles of ammonium ion, what's going to happen? Well, I have a limiting reactant problem. I've got ammonium ion and I've got hydroxide ion. I've got 0.65 moles and 0.2 moles. Which is the limiting reactant? The hydroxide. There's only 0.2 moles. So how much of the ammonium ion am I going to react? 0.2 moles. How much will I have left? 0.45. I'm going to react all of the ammonium ion using up the hydroxide. What's my ammonia concentration now? It was 0.7. But I've just reacted 0.2 moles of hydroxide with that 0.7 moles of ammonia. So now how many moles of ammonia do I have? 0.9. Guess what? You've just finished the limiting reactant part of the problem. And if you think back to October when we first did limiting reactant problems, and they were so mystical for some of you, now you don't even have to do the calculations on paper. You can do it in your head, I hope. If you're still struggling with it, keep practicing. But if I look at the reaction and I say, oh, I know the hydroxide is going to react with the ammonium ion, using some up and making some of this, now I solve the equilibrium problem. The next question everybody comes up with at some point is they say, how do I know which direction the reaction is going to go? Okay? You can either calculate Q, or you can say, just a second, Emma, or you can say, do I have everything I need for the reaction to proceed in a certain direction? So if I look at this one over here, I have ammonium ion, but I have none of this. Can this reaction possibly go that way? No. You don't have anything to react with. I have ammonia. Do I have water? Anytime you see a charged ion, you better have water. So yeah, you have water. So you have both of these, so you can go this direction. That's how I know this was plus and this is minus. Now if we say, I'll finish that one in a second. Now if instead of adding sodium hydroxide to this buffer system, I add HCl to the buffer system. That one? That one? Okay. When you're given a buffer system, as I said, you have to ask yourself, what equation should I use? I will encourage you, now that you know it doesn't matter whether I start with the base or the acid form of this buffer, I'm going to get the same answer. Write them both. Only solve one, but write them both. Why should you write them both? Because then when you get to part B of the problem where it says, now add 0.2 moles of sodium hydroxide, you don't have to say what does the sodium hydroxide react with, because it's written there, right there for you. It reacts with the ammonium ion. And if instead of adding sodium hydroxide I had said add 0.2 moles of HCl, you don't have to say what does it react with, you just read it off the board. It reacts with the ammonia. So if you write both equations, you'll never question yourself as to what it reacts with. After the test next week, we'll get into the fine details of what it reacts with. Right? Today, this is good enough. If you think about it, it's really not tough. So that's why I have you write both the equations. And you can solve either one.
So if it was HCl, what would that look like?
Let me finish this and then I'll show you. Because again, it doesn't matter which reaction I use. We've already said that. So now that I've picked this one, I fill in the ice table. Because OH minus is a product, I know this is a Kb. And it equals that. Kb was given to us originally in the problem. It's 1.8 times 10 to the minus 5. I'm going to skip a small step here where I assume that x is small. So if I assume x is small and then I bring this to this side of that, I get this. Anybody do this one in their head for me? 0.9 over 0.45. It looks like 2. 2 times 1.8 is 3.6 times 10 to the minus 5. So that's the OH concentration. The POH equals 4 point, I'm sorry. And the pH equals 9.56. Did the pH go up? Yes. So are we confident we did it right? Yes. Okay? Everybody okay with that? Now, what if instead, someone said, we added 0.2 of a mole of HCl to the original reaction? Well, now we come back to our two equations and we pick the obvious one. HCl reacts with ammonia. By picking the obvious one, the limiting reactant problem becomes a piece of cake. 0.2 moles of HCl, 0.7 moles of ammonia, they're going to react 1 to 1. So when it starts to establish equilibrium, what's the concentration of ammonia? 0.7 minus 0.2, I hope. There, we're done with the limiting reactant part of the buffer problem. Anybody want to tell me the answer without doing any more calculations, by the way? 9 point what? 9.55? Nah, I doubt it. Uh-oh. Why do you think it's 9.02? Wouldn't the change in pH by adding 0.2 of a mole of sodium hydroxide in the positive direction be exactly the same as the change in pH if I add 0.2 of a mole of HCl, but in the other direction? Absolutely. If I did this to you on a test, those of you who got this stuff would say, oh, here's the answer. You wouldn't have to show me your work. You'd just say, it has to change by the same amount. Well, let's prove it to ourselves. So you think it's going to be 9.02? Let's check it and see. We've done the limiting reactant problem. Now it's just an equilibrium problem. I'll skip that. I'm taking shortcuts. Hopefully the algebra is comfortable enough now I can take some of those shortcuts. You can see where it was. I just substituted the value of Ka that I knew. I assumed x was small. I brought this to the top and that to the bottom. And so x equals 5.4 times 10 to the negative 10. 5 point what? 9.4. That's better. Times 10 to the negative 10th. And that's equal to the hydrogen ion concentration. So the pH is surprise, surprise. Can I do that on the test and just not point it out to you? If you come prepared to do that, you may be happy. What if I added 0.3 moles? Could you tell me the pH with doing a very simple calculation, not doing a nice table, of acid? What would the pH change if I added 0.3 moles? First of all, it's going to be less than 9, right? It's got pH has to go down. How much less? How did you just figure that one out? You said if I added base, it would go up the same amount as it goes down. Why'd you get 8.86?
I just found the amount it would change. It changed per 10 moles added.
Okay.
And then multiplied by 300.
The change in pH here between the initial pH and this was 0.26, right? And that was for 0.2 of a mole. If I have 1.5 times that, what do you think the change will be? I hear a phone ringing, by the way. 1.5 times that, 0.26 times 1.5, 0.39. Subtract that from 9.28, and you get 8.89, 8.86. If you try it, you'll find out it's right. Because it's a very linear relationship as long as what's true? The definition of a base is that they're relatively equal amounts. It's when you get outside of that relatively equal amount range that you can't do that anymore.
So if you're adding HCl, like, what happens to you started with NH4Cl?
What happens to the chloride? Let's see, the solubility rule for chlorides is they're all soluble except silver, mercury, and lead. So guess what? Chloride's just floating around in there. Doesn't change. Chloride is a neutral ion, remember? It's the salt of a strong acid, and so the salt of a strong acid is neutral. The limiting reactant? I can do that. Let's see. All right, if I go back to that one over there, where I started with 0.7 moles and 0.65 moles. The limiting reactant part of that of NH3. All right, so here's my buffer. It's a mixture of a weak base and its conjugate acid. I add acid to it. One of the other things you can think about, if you don't have the equations, you can say, okay, if I'm adding an acid, it must react with a base. So if it's going to react with a base of these two, which is the base, ammonia, and so if it reacts with the ammonia, it's going to use, we have to do a limiting reactant. So let me do the long and gory details. That's the mathematics of what we did in our head. You can see why I said, we don't have to do this anymore. You can all do this in your head. Once you understand how they work, and the fact that for all of these reactions, they're monoprotic or monobasic. 1 mole reacts with 1 mole. As soon as you make it diprotic, you cause problems. But I'm not going to do that to you. Because if you think about it, think about carbonic acid. The most important buffer system you could ever study is the carbonic acid buffer system. Why? Because if the pH of your blood, which is regulated by the carbonic acid buffer system, changes by, what is it, 0.3 of a unit, you will die. Your pH, your blood pH has to be very well buffered. Because if it changes too much, you will die. It's that simple. And so carbonic acid is the buffer system that works in there. Well, what is carbonic acid? H2CO3. After we show you this, you're going to say, well, why don't we talk about carbonic acid as a buffer? Why do I let the biologists do it? Carbonic acid is diprotic. There are 2 acidic protons on every carbonic acid. Does it really dissociate in 2 steps? Maybe. More likely it dissociates in 1 step. So the question is, why do we separate it like this? We separate it because it's much easier to study. We can look up the Ka values for these. Anybody have their table with them handy? I didn't bring it. Susie's got it, thank you. I hope carbonic acid is listed in there. I think it is. Did I get you, Max? Oh, let me try again. All right, let's see. Carbonic acid. Oh, Monday we're going to talk a little bit about indicators, by the way. We're going to do samurai chemist. We're going to have fun. Where is it in here? Oh, by the way, I can also show you the Henderson-Hasselbalch equation now because it should make sense. Yeah. I don't know yet. Read the whole thing. We'll get to it. I can't find it. I'm going to make up the numbers. It's in chapter 16. Did you not bring that? Look for the Ka values for carbonic acid. Let me ask this question because it sets it up nicely. Well, actually, there's a couple. First of all, there are 3 ways to make a buffer. And I know what you'll all say is the number one way to make a buffer. Buy it. I will accept that as a partial credit answer on the exam. I guarantee you there will be a question on the exam that says, make a buffer of this pH. And if you tell me you're going to buy it, I'll give you partial credit for that. Not full credit. I'll even tell you how much partial credit, probably 2 points out of 10. Unless you can tell me the stock number and the price of the buffer. So I can tell you're all going to bring in a sheet from a catalog. Never mind. So you can buy it. That's one way. What's the second way? You can add a strong base to a weak acid. If I add sodium hydroxide to ammonium ion, what do I make? I make ammonia. If I've got ammonium ion and ammonia, what do I have? A buffer. How much of the ammonium ion should I neutralize ideally? Half of it, because I want relatively equal amounts. Those of you who've had lab, why did you go to the half equivalence point? What is the equivalence point? It's when the moles of acid is equivalent to the moles of base. If you're at the half equivalence point, you've neutralized half of it. So if I neutralize half the ammonium ion, I have an equal amount of ammonia. I now have a perfect buffer. That's as good as I can get. That's the second way. What's the third way to make a buffer? No, we already said buy it. You missed that one. Well, how do I get the equivalent pH to the pKa? I want equal amounts of ammonia and ammonium ions, so I take ammonia and I take ammonium chloride and I dump the same number of moles in. Yes. So I can make a buffer by buying it, by neutralizing a weak acid or weak base with a strong base or strong acid, or by mixing equal amounts of the weak acid and its conjugate base. Those are the three ways to make buffers. Did you find them, Susie? What'd you get? For which? Ka1 or 2? Is there a Ka2? There is no Ka2? How about HCO3 minus? 2.4 times 10 to the negative what? All right, there's carbonic acid. Your blood pH is approximately 7.3, I think. Which of these two dissociations matter? The first one or the second one? The first one. The first dissociation, if you take the pKa, who's got their calculator out still? 6.4, really? Okay, I'll believe that. And this pKa would be what? Close enough. If your blood has to be buffered at about a pH 7, it's only that first one that matters. The second dissociation is not going to contribute to the buffering capacity of the blood. Now, is there more bicarbonate ion or carbonic acid in the blood? If the blood pH is supposed to be about 7, is there more bicarbonate or more carbonic acid? Bicarbonate, because we want the pH to be higher than 6.4, so we need more of the base. Okay? Bicarbonate is extremely important for the functioning of your body. What do you take for acid indigestion? Sodium bicarbonate. Why? Because you got to neutralize that acid and get it back to the right pH. And so sodium bicarbonate's already in there. Add something you've already got. What if you add sodium carbonate? What is sodium carbonate? Baking powder. Baking soda is sodium bicarbonate. You can make an antacid just by taking a little baking soda, putting it in water, and drinking it. It doesn't taste real good, but it'll do the job. Baking powder is carbonate. And will it still do the same thing? Yes, it will. But now you're way over here at this very basic ion. You could also have a little chalk. Don't do that. I've done it once or twice already, right? That's enough. Somebody told me Butler does that. What's wrong with him? He doesn't, I know it. He's barefoot up here too. So, all right. Monday we're going to talk about exactly what's on the test. I'll have it written. What's on it from chapter 18, and we'll be doing indicators. Oh, I got to keep telling you about the assessment. I'll tell you about that Monday. You aren't going to get your papers back till you've graded your partners.